Welcome back, students, and let's do some area problems associated to definite integral. And these are going to be geometric area problems. Area between curves. Let's suppose we have these kind of curves. And basically what we want is the bigger area minus smaller area. You see? Shift them up appropriately. And whatever it is, we can make both graphs positive. Okay? And then do the area computation. Upper area, which goes above the axis all the way to blue. And then lower area from the x-axis to brown. So this one goes to blue, and this one goes to brown. Subtract one from the other, this plus m shifting cancel out, we end up with u minus l. So what's the end result? It doesn't matter where the graph is, where the x-axis is. Area is just upper function minus lower function, that integral. Okay? If both had been above the x-axis, then from this kind of graph, it would have been easier. Bigger area, which comes from blue all the way to the x-axis, minus small area, this white part, brown to x-axis. Bigger minus smaller, and then you get a middle area. But in general, how do we do that? Even in general, it still works because all you have to do is shift them up a little bit with plus m and move it up and then do the same thing. If you follow all that, great. If you don't, just consider it as a formula. Integral of upper function minus lower function. If you have more than one regions like these, intertwining regions like this, in that case, if you calculate the integral, then this part will be positive, that part will be negative, this part will be positive again, things like those, and then we have cancellation, you're going to get a mess. So you'll have to consider each of these shaded with different colors separately and calculate upper function minus lower function separately and then do your computation. Yeah, complicated. But in reality, we have considered upper function minus lower function separately for first region, second region, third region, and then if you have 15 regions, do those separately and then add them up. Because those are just elementary computation, just adding up. And if you can do about 2 of those, then we'll assume, oh, okay, just repeat it 17 more times, then you can do everything. So people don't really bother with all kind of complicated graphs. Just twice, just one blue and one red, and that's where people stop. You won't have to consider any more complicated problems in regular problems. Let's see, do we have some example problem here? Region bounded by a curve like this. Oh, wait a minute, this is a problem we already did. Integral of 1 minus x squared. Remember this? Plug in the top, plug in the bottom, subtract one from the other. Okay, all right. Really simple problem. And by the way, another solution is by Archimedes, kind of like this. Get a triangle, and get next triangle, and then the next triangle, and so on and so forth, and then add them all up, and then you end up with 4/3 anyway. And oh boy, I did the computation here. What was I thinking? In the end, it turns out 4/3. Archimedes did it because he was genius, but I do not assume that kind of geniusity to everybody. Okay, let's go to the next problem. Some quadratic functions. If you graph those, we get graph kind of like this. So what do? Upper function minus lower function. So this is the upper function, blue, and that's the lower function, red. And if you plot those, you'll see. So the area is gonna be the integral -2 to 3. And the upper function is going to be 3x squared plus 4. And the lower function is 1 plus 4x minus x squared. And this is blue, and that's red. And all you have to do is to calculate this integral. It'll require a little bit of tedious computation because you'll have to break up parentheses and take the like terms together and do your computation. But if you do everything and then plug in the top, plug in the bottom, subtract one from the other, you're going to get the answer. Well, here's a computation. Oh, looks like there must have been a typo. This should have been 2x squared minus 4. Okay, all right. Sorry about that. I'll correct it in the real version. And then do your computation. Break up the parentheses and like terms together, and then you get this. All right. And then go ahead with the anti-differentiation. Apply the fundamental theorem. And then calculate, you get the answer. Now here, the first step is essential because this one gives you the area formula, upper function minus lower function. And then this step, oh, this one is essential too. We have a bunch of power function added up, so you cannot skip this. Antiderivative, that too is important. And fundamental theorem, of course that's important. And the final answer, okay, maybe not that important, but yeah, looks like there's nothing you can skip in this kind of problem. Usually, it's not a good idea to skip anything, actually. Let's see, do you have time for areas for infinite regions? Like this? Okay, this one goes on forever, but with horizontal asymptote at the y equal to 0, so if this goes down quickly enough, then we may have finite area. We can find out by calculating the antiderivative and in the end doing the limit computation as going to infinity. Up to the task? Okay, go ahead. Set up the integral. Upper function, exponential, minus lower function. Lower function is y equal to 0, so you don't really have to consider. So here's a function. And if you calculate the antiderivative, oh, this is just simple antiderivative computation. All I need is 1 over a, so 1 over negative a, 1 of negative 2, excuse me. And then that simplifies into negative 1/2. And then plug in the top, plug in the bottom, but plug in the top, e to negative infinity is 0. So we end up with a finite area. How about the next problem here? Region bounded by this. Again, plot the graph. And we have this, we have vertical asymptote here. But if this graph approaches to this y-axis quickly enough, then there's a chance it is finite area. We'll see. Calculate this integral, but that's a lower function. 0 minus of that, so it's gonna be negative of that computation. And let's do the computation. Separate the numerator, and then simplify each. Calculate the antiderivative of each. And then fundamental theorem. Plug in 1, plug in 0, subtract one from the other, and we got the answer. Oh, we ended up with negative value. Does that mean everything is wrong? No, not really. I mean, look at the picture. Naturally, we are going to get negative number as assigned area. And we are looking for a geometric area, so just take the positive. Take the absolute value to make it 2. So that's the area. No need to panic. So, sometimes, when you're lucky, you get a finite area even from unbounded regions. For infinite regions, you can still get finite areas. Not always, but sometimes you do. In that case, it may show up in the exam. In the exam, okay, all right, there's some chance, but not a whole lot of chance, I have to agree. I mean, the chance is pretty low, but it's not 0. Okay, all right, that's where I'm gonna complete. Area problems done, but please accept it with some grain of salt, basically. This is a kind of thing that you study after covering everything like a blanket. For example, if you're totally comfortable with this kind of example problem, absolutely comfortable, and then if you want A in the class, all right, then you may study some example problems like these, especially down here, these. Okay, that'll complete everything.